Hi everyone, welcome back to Math 112. This is Scott. Let's get started. We have now successfully finished Chapter 5, and we are on to the next topic, which is in Chapter 6, and that starts by a consideration of inverse trigonometric functions. So we start in 6.1 with the inverse sine, cosine, and tangent. We'll just start with our three favorites, and then we'll deal with the other ones in section 6.2. So the inverse sine, cosine, and tangent functions. Alright, so first off, let's try to remember what inverse functions even mean. So recall, an inverse function and we can write f inverse like that. We typically write inverse functions with a little -1 up in the superscript. It looks like an exponent, but it's not. Is a function that switches the roles of input and output. From the original f. Now, when that all goes according to plan, that's all well and good. But sometimes there are some complications. So, in particular, only functions that are, as they say, one-to-one are even invertible in the first place. And none of the trigonometric functions, it turns out, are one-to-one. So, there's a specific caveat that we have to have here. So note, in order for the inverse functions for sine, cosine, and tangent to be well defined, meaning you get a straight answer out of it when you try to plug something in, in order for them to be well defined, each of them is restricted to a specific range of outputs. Now the general layout, so in general, what's happening here is that we plug in now the value of a sine or a cosine or a tangent, and then this will give me the angle within the specified range that matches that value. So in general here, so the input will be so these are for the inverse functions. The input will be what used to be the output. So in other words, the sine, the cosine, or the tangent. So the value of the sine, cosine, or tangent. And now for the output, what we will get is the specific angle that is within the appropriate range, which has that value. So this is the angle in the correct range that achieves that value. Alright, so let's talk first about sine. So inverse sine. So inverse sine. So this is also called the arc sine. And that's the way you'll see it frequently in calculus courses, is as the arc sine formulation, inverse sine. We write, so the notation is sine inverse, written like that. So when you first saw that on a calculator, maybe you thought that that referred to the cosecant, but actually what it is it's the inverse function. So notation like this, or like this, arc sine. Oops, or actually just arc sin, like without the e. So this is what you'll see in this textbook. Other textbooks you might see this. Occasionally you might see a sine, but that's a little bit less common. So then, sine inverse, you put in right here, in goes the number, and it represents the sine of an unknown angle. So this is a number between -1 and 1. And then the answer over here, so this is going to be an angle between -pi/2 and pi/2. So you plug in a number, you get an angle. And for sine, the angle that you're talking about is between -pi/2 and pi/2. So that represents the right side of the unit circle. So this represents the range of sine inverse. Okay, and the reason for that is that sine represents the y values of the unit circle, or y/r if it's not a unit circle, and those are all found on this side, and they're just repeated on the other side. Okay, so that's inverse sine. Inverse cosine, or arc cosine. Again, the notation is cos inverse, or arc cosine. And then what it gives, So what it gives is an unknown angle that achieves some cosine. So this will be a number between -1 and 1, and it will equal, over here, an angle between 0 and pi. So this means, in other words, the upper half of the unit circle, because now we're talking about the x values, and all of the x values would be on display if we just look at the values that go from 0 to pi. And so it is the upper half of the unit circle. And then finally, inverse tangent. Or arctangent. By the way, the reason it's called arctangent, arcsine, arccosine is that if we think about the angles as representing arcs of a circle, which is what radians are all about, then we're telling you the arc length if you give us the sine of the cosine, or here the tangent. And the notation is, of course, tan inverse, or arctan. And again, let's just think about what can go in and what will come out. So what can go in is anything that would traditionally be the output of tangent, but remember the range of tangent is actually all real numbers. So this can be any real number. Whereas the output is only going to be specifically from -pi/2 to pi/2. So this is an angle between -pi/2 and pi/2. And this would be very similar to sine, except that here the -pi/2 and the +pi/2 are actually technically not included. It's not a big deal, but it is worth mentioning. So there's like an open circle, because at those points themselves, tangent is actually undefined, you'll recall. Okay, so this is the range of inverse tangent. Now, for the simple start of these exercises, we'll just have you literally evaluating the inverse functions to begin with. Evaluating these functions. So the basic idea would just be figure out where we are on the unit circle, and then we'll know the angle. So try to recognize the value as a known angle on the unit circle, and then just find the version of that angle that is in the correct range. Let's just try some examples. So a helpful fact. So useful fact. So we could find this by rationalizing denominators and things like that, but it is just useful to know that facts. Useful to know a couple things about tangent. So first off, the tangent of pi over 6, that's equal to root 3 over 3. The tangent of pi over 4, that's equal to just 1. Because remember, that's a 45-degree angle, and that's where the slope is 1. And the tangent of pi over 3 is equal to just root 3. So you've actually found each of these individually at some point by just, putting the y over the x and rationalizing denominators and things like that. But it turns out, actually, it's useful to just have these stored away in your memory. Okay, now let's try some examples. All right, how about something like the cosine inverse of 1. Cosine inverse of 1. So let's just think about this. Cosine, that means the x value on the unit circle. And so where is the x value equal to 1? That'd be right there. What angle is that? That equals just 0. All right, let's see if we can do another. How about the cosine inverse of negative 1? Start by sketching yourself a little circle, and then ask yourself, okay, x or y, and that equals negative 1. So here, the x is negative 1, so that's going to be at the angle of pi. Alright, how about something like this? What if I asked you about the sine inverse of negative root 2 over 2? Well, first off, root 2 over 2 is a familiar number to us. We recognize that as being the coordinates at the 45-degree mark. The fact that it's negative, though, means we're down here. Now, the most important thing about this is, especially when we're not in quadrant 1, make sure you are giving literally the version of the angle that sine inverse can, which is the version that is between negative pi over 2 and pi over 2. So it would not be correct. It would not be correct to place this angle as 7 pi over 4, even though technically that angle is coterminal with the one we want, but our answer literally has to be between negative pi over 2 and pi over 2. So this must be in negative pi over 2 to pi over 2. So you cannot give another version of the angle even if it comes out with the same sign. How about tan inverse of negative root 3? Well, negative root 3. So that one was one of the 30, 60, 90 angles. And if we think about it, so root 3 over 3 is smaller, root 3 is bigger. And so that means we're talking about a steeper slope, here negative. So we're talking about the lower one here. So that means this angle down here, and so we must be talking about negative pi over 3. And again, the answer must be whatever the version of the angle is that is between negative pi over 2 and pi over 2. The only difference between tangent and sine in this regard is that tangent doesn't include the endpoints. Okay, but you get the idea. So you just have to figure out where on the unit circle it is that we're talking about, and then you just have to find the version of that angle that makes that happen. Now, If you are evaluating these things in a calculator, it is paramount to make sure that you have it in the correct mode. So to evaluate these functions, in a calculator, pay close attention to the mode. And in particular, for us, we are going to always want the mode here to be in radians. So here, radians. Will be the default. Okay. So just as a quick example, let's say I wanted to evaluate something. Maybe I want to evaluate so let's say evaluate and round to 2 decimal places. And let's say I just wanted to do inverse tangent of 10. So remember, any real number can be the input for an inverse tangent because any real number is capable of being the output of regular tangent. So the way you do this in your calculator, first you make sure it's in the correct mode. If you have a calculator like this, the DRG is how you change the modes, degree, radian, radian. What's that stand for? Alright, so if we are in the right mode, then we just enter and we're good to go. So now you just find the button that has the inverse functions, and those buttons will usually be the same button as has the original trigonometric function. So here it would be that one right there, tangent inverse of 10. 1.47. 1.47 to these 2 decimal places. And then let's say, I don't know, sine inverse of 0.7. And if I'm rounding it to 2 decimal places, it's 775. So the next digit is bigger than, is 5 or larger, so we round up. So it'd be 7, 8. And then, just as a last one, let's have a trick question. Trick question. Cosine inverse of 1.5. Here I go. Not suspecting any trick has been played on me. Cosine inverse 1.5. Enter. And we get a domain error, and that is exactly what just happened here. This was not in the correct domain. So this is undefined. Okay, so this is not in the domain. Remember, if we are thinking about a unit circle, cosine is the x value. Find me the x value on the circle that is 1.5. Good luck. Okay, now let's discuss the next issue here, which is the evaluation of compositions of functions. And there are two main formats here. two formats are, we'll have the function on the outside and the inverse function on the inside, or we'll have the reverse. We'll have the inverse on the outside and the original on the inside. Now, in either case, we're basically just going to work our way from the inside out. But here specifically, this starts us with a trig ratio. That's a trig ratio, so it has to be in whatever the appropriate, it has to be an appropriate value for that. So if this is a sine, you have to have a number between -1 and 1. If it is a cosine, also -1 and 1. If it's a tangent, though, it can be anything. And then out here, so this will produce the trig ratio. So this is the trig ratio. This turns it into an angle, and then this turns it back into a trig ratio. And then this one in here will have to be the angle. And essentially, the basic approach will be just work your way from the inside out. So the approach in both cases just work from the inside out, and then just evaluate each piece according according to its unique domain and range. All right, let's just try this. So let's just try something like this. So what if we have let's just say we have the tangent of the inverse tangent of 10. Well, what's going to happen here is that when we do the inverse tangent of 10, this will give, so this gives an angle. It's an angle in -π/2 to π/2. And then this will then give the tangent of that angle. And so what we can see is the tangent and the inverse tangent are actually just going to be undoing each other and returning you back where you started. So this is what will typically happen when we do this. So what will usually happen fall into three main categories. So the three main things can happen. One, if the values are already in the correct ranges, the function and its inverse will just cancel. 2. If the values are not quite in the right ranges, but not in a way that's undefined, then if there's a slight mismatch, we try to find the angle in the correct domain that shares that trig function value. And an example of something like this might be, maybe we have cosine inverse of the cosine of negative pi over 4. Now what's going to happen here is when we start evaluating these things, the negative pi over 4, we can certainly plug that into a cosine, but it's not going to be the one that the inverse cosine would give as the equivalent answer. So as we evaluate this, we get cosine inverse really of, and then we just crunch the numbers here, and this is the x value, so that's root 2 over 2. And then just working our way still from the inside out, we just look at root 2 over 2 and pretend like this is a fresh question. And so they didn't quite cancel each other out exactly, but the angle was converted into an angle that is in the correct domain, which shares the same cosine as negative pi over 4. So that's going to be positive pi over 4. So the angle ended up getting moved into the right domain. Now, note. One note about that. So this is a note within a note. So subnote. We can even do this for angles whose sine and cosine are unknown to us. Using the symmetries of the unit circle. So for example, so actually here, let me point out the two useful symmetries that will come in handy here. If you have some theta and you don't know its sign, but you know that it's in the wrong spot, like let's say it's over here, so this is just some random angle, let's call this theta. Then if we want the angle over here, the angle that has the same sign, it's going to be pi minus theta. And this has the same sign. that's going to happen. This is going to happen when it's a sine that we want to use. Let's say it's a cosine, and our angle is down here. Or just to avoid confusion, I'll write this one as negative theta, and this one will be positive theta. So theta and negative theta have the same cosine. And then lastly, if it's tangent, then most likely what you just need to do to get yourself into the right quadrant is just add pi, or subtract pi, whichever is more convenient. Let's say your theta is over here, wrong quadrant. Here, this is just using the fact that theta is periodic, and you can just say, whichever is more convenient. You can say theta plus pi, or theta minus pi, if the numbers would make that a little bit nicer. And those both have the same tangent as theta, because theta is periodic with period pi. Okay. And then final category. The final category is if there's a major issue, then you might actually just be talking about something that's undefined. Final category is this was number 3. The inner function might not be defined for some input. And a good example of that would be, let's just say, cosine of cosine inverse of -2. So this is undefined. You ideally want to try to cancel things out. If you can't cancel them out directly, then you move them to the appropriate spot, and then the only thing that can really go wrong is maybe the input that you put in there is not actually even defined in the first place. Alright, let's now put these all together and do some more examples. So we'll see some examples of all the things that fall into one of these 3 categories. Okay, so let's start with something relatively easy here. And we'll just say cosine inverse of the cosine of 4 pi over 5. Okay, so the most important question that you have to ask yourself is, will this function and its inverse just cleanly cancel each other out? That's the hope. And they will cleanly cancel each other if the number you have been given is already within the appropriate range of cosine inverse. So 4 pi over 5, that is not one of our friendly angles. But we can think about it for a second. So if this is pi, then this would be 4 pi over 5, somewhere around there. And even without knowing what the actual cosine of that angle is, I can still actually tell that it works out because that's actually in the range. So this is in the range of inverse cosine. And so that means that these just cancel, so they just cancel. This is like the ideal case. So this just equals 4 pi over 5. Now, what if, though, exact same question had been asked, but cosine inverse of the cosine of 6 pi over 5? Well, then we'd be in a different situation now, because now we are looking at an angle that, instead of being just a little bit below pi, is a little bit above pi. And so this is our angle here. And so they don't exactly cancel each other out, but what they do is so the answer will be whatever angle this is that has the same cosine as 6 pi over 5. Now, right here, we can so we could see you can see different ways of thinking about this. 6 pi over 5. So this has the same cosine as negative 6 pi over 5, which is in the right spot, but it's not the right version of that angle. So this is in the right quadrant. So it's in the right quadrant. I should say correct, because it's actually in the left quadrant. But it's in the correct quadrant. Wrong version of the angle, though. In particular, the thing that's wrong about it is that we're not supposed to be getting a negative answer for an inverse cosine. So we can add 2 pi. That's a coterminal angle. And so it's going to be 10 pi over 5 minus 6 pi over 5 leaves us at 4 pi over 5, which in fact makes a whole lot of sense. So this is the same as, in fact, 4 pi over 5. And that's the angle in the correct spot, in the correct format, that whose cosine is the same as this. So all together, this was all just, work to the side, and our final conclusion is still 4 pi over 5. So if everything is in the right quadrant and in the right form, then they'll just cancel each other. If it's not in the right quadrant, then you have to just figure out what angle corresponds to it, which is in the right quadrant. And sometimes these will just be like known angles that we have some familiarity with, and other times they'll be a little bit more off-kilter angles that we're less familiar with. Let's just try one or two more here. So how about one with the function on the outside, the inverse on the inside? How about the I keep doing cosine. How about sine? Sine of sine inverse of, and now here, as long as the number that we're given is in the right range, then we are fine. Let's say it's negative 2 over 2. So if it's in the right range, we are fine. And the right range here, the right domain of sine inverse is everything between -1 and 1. So as long as that number is in there, we're good. So they just cancel. And sure enough, root 2 over 2 is within the appropriate range. And if you evaluate this from the inside out, you actually just get, so what you get is, first you would just say, okay, the angle whose sine is root 2 over 2 is pi over 4. Then the sine of that angle is root 2 over 2. find something like this. So sine of sine inverse of 2 is undefined. And that's because the sine inverse of 2. That's where it breaks. Okay, now last topic of 6.1 is to find inverse functions for more general trigonometric functions. Finding inverses. So, for example, maybe what we have is something like f of x is equal to 2 sine x plus 5. And then we'll be given a specific domain. Negative pi over 2 to pi over 2. So this is our function. This is the domain. Okay, now this is actually the general procedure that you will use to find inverse functions. So here's the basic idea. So find the formula for f inverse by. So this is the general procedure, and it all comes from what inverse functions really mean. So an inverse function is a function that switches the roles of the input and output. So literally, what we will just do is switch the x and the y. So right, y equals 2 sine x plus 5. Then switch x with y and y with x. So that means x equals 2 sine y plus 5. And then solve for y. Solve for y. And when the time comes when you have to undo the trig function, you undo the trig function by using its inverse. Use the inverse trig function to cancel. The trig function. So here would be an inverse sine. Then when all is said and done and you've done your algebra, then find the range of the original function along with its domain and the domain is something will be given, and then switch those to get the range, or sorry, the domain and range of the inverse. In particular, if input becomes output and output becomes input, then domain becomes range. So the domain and the range of f and f inverse just switch. So the domain of one is the range of the other and vice versa. So back to our example here. Let's actually put that in play. And we'll just now upgrade that to an actual example. So find f inverse, find its domain. So our function was f of x, which equaled 2 sine x plus 5, and we were given an initial domain for the original function of negative pi over 2 to pi over 2. Alright, so let's give it a try. So first off, we write it in terms of y instead of f of x. And the reason we do that is so that we can now execute the switching of the input and output. So x equals 2 sine y plus 5. And now what we do is we just work our way to the y by removing everything from around it. Subtract 5 from both sides. And then divide both sides by 2. And now we've come as far as regular algebra will get us in undoing everything around the y. But now what we need is to use the trigonometric function inverse sine. Sine inverse, arcsine. So one way you can just write it is you can just rewrite the whole thing as y equals sine inverse of x minus 5 over 2. And that is what the inverse would be. And you can think of what happened from here to here in one of two ways. One way of thinking about it is you just literally switched the function to its inverse function, which switched the original input and output around. Alternatively, you can think of it as you applied the inverse sign at both sides of the equation, and that canceled the sign. Now, when it comes to the original f, we can find its domain and range. I mean, the domain is already given to us, and its range we can find by just reasoning it out. So the domain is right here, negative pi over 2 to pi over 2. Didn't require any work on our part. And then for the range, we can just think about this. This is a sine function, so it has an amplitude of 2, and it has a midline of 5, which means then that the maximum is going to be the midline plus the amplitude, and the minimum is going to be at the midline minus the amplitude. And so that gives us a range of 3 to 7 for the original function. And now for f inverse, the whole thing just is switched. Three to 7 is now the domain. Negative pi over 2 to pi over 2 is now the range. So that's how that could go. Let's try one with a tangent here, just because that involves something a little bit different. So let's say f of x is equal to tangent 2x minus 1. And let's say that the domain that we are going to be given here is going to be negative pi over 4 to pi over 4. Alright. Now, the way we do this, it's all very stereotyped. We just start, we replace the f of x with a y, just so that we have a y in here. Then we switch x and y. Now we solve for the y, and we just work our way from the outside in. So outside, so we add 1 to both sides. Now we apply the inverse tangent to both sides to get rid of the next layer in. So tan inverse of x plus 1 equals 2y. And then finally that means then that y is equal to, the easiest way of writing this, by the way, might be to make it 1/2. Multiply both sides by 1/2. Easier than making big fractions out of things. And tangent of x plus 1. Now, when we think about the range of the original function here, this is a tangent. And tangents swoop all the way up and all the way down, so all real numbers. So when we make this little schematic of domains and ranges for f and f inverse, we have given to us the domain of the original f, negative pi over 4 to pi over 4. And the original f has a range that is all real numbers. So if we want to do that in interval notation, which is the way your Pearson MyLab thing wants it, then it would be negative infinity to infinity. And so then by the same token over here, the roles will reverse, and it's now the domain that's negative infinity to infinity, and it is now the range that is negative pi over 4 to pi over 4. Alright, so that's the deal with tangent. The most important thing about it, just remember, is that tangent range is goes from all the way from negative infinity to infinity. Alright, and then the last example of something like this, this will be just part C. Last example will be a case where the domain looks a little weird, but we don't do anything any differently with it than we did before. So let's say we have f of x equals 2 cosine parentheses 3x plus 2 into the parentheses. And now the domain that we're going to be given here is negative 2/3 is less than or equal to x, which in turn is less than or equal to negative 2/3 plus pi over 3. Now this looks like this looks a little different. It looks a little odd, maybe, but it's the kind of thing that will frequently happen here. It's the result of having basically a mismatch between the numbers here and here as far as the period versus the shift. Okay, but we'll deal with that when the time is right. Till then, what we just do is the same old process. So we just work our way from the outside in. Here, the only thing on the outside is that 2, and so you can just do it as y over 2, or you can do 1/2 y. Either way. I like 1/2 y usually. Cosine 3x plus 2. And then to undo the cosine, you would do the inverse cosine. And that'll cancel the cosine from the right. And then we subtract the 2. That's being subtracted from the whole outside here. And then finally, we divide by 3. Oh, sorry. So I never actually switched the x's and the y's around. So sometimes actually, by the way, it is not customary to do that. Sometimes you would actually just leave them the way they were, and you would actually just keep x standing for what was originally the input and y for what was originally the output. But that's not the way we'll operate here. So we will switch them. Different books do it different ways. So again, every x and every y are now switched because we are now in the inverse. Alright. So now that means f inverse of x equals cosine inverse of 1/2 x minus 2 all divided by 3. Okay, now let's think about the range here. So the midline is 0, and the amplitude is 2. This is a cosine, so that means -2 to 2 for the max and the min. Alright, now, once again, we just make our little array here, domain and range. So here, the domain is going to be just this kind of weird looking thing, -2/3, comma, -2/3 plus pi over 3, and the range will be -2 to 2. On the other hand, when we're talking about the inverse function, these are just switched, and this becomes -2 to 2, and these become -2/3 to -2/3 plus pi over 3. Alright, and that concludes section 6.1. The next section we'll be building off of this foundation to introduce a little bit more in the way of the inverse trig functions. And now the exciting second part of our two-part lecture here, 6.1, 6.2. In 6.2, we are going to extend the inverse trigonometric functions to include our other three friends. Alright, so in other words, we are now going to be defining the inverse secant, cosecant, and cotangent. So secant inverse, or arcsecant. So this will be the angle between, so in this one, 0 to pi, so matching cosine, and the only exception will be at pi over 2, where secant is undefined. That has the specified secant. Cosecant inverse. Same thing, but you just have to know what the specific range is. And the ranges here are modeled on the sine and the cosine. So the angle between negative pi over 2 and pi over 2. And here again, except 0. That has the specified cosecant. And then most importantly, for cotangent, if you can imagine what the inverse function to cotangent would be like. The only question is, what will its range be? And here, this one is the only one that's really different from its parent function. This is the angle between, and here it is 0 and pi. Not included. Not including. The endpoints. That has the specified cotangent. Now the general philosophy for evaluating these things will be to rewrite the expression in terms of sine or cosine or tangent. So our general strategy will be to rewrite anything involving the reciprocal functions in terms of the basic trig functions. So as an example, so let's say I wanted to evaluate something like this. Evaluate inverse secant of 2. So if I had said the inverse cosine of 2, then it would be pretty hopeless because that'd be undefined. Here, however, this is defined, and the best way to think about it is just rewrite it as saying, okay, so the secant of some mystery angle equals 2. And now, what does that mean? That means 1 over cosine of that mystery angle equals 2, which then, if I multiply both sides by cosine and divide both sides by 2, I would get 1/2 equals cosine theta, which means that which means that theta, which is what I've just been calling this angle, so I have something to write, is equal to cosine inverse of 1/2. So that now I can evaluate. So when I try to do that, it didn't work, but I can certainly do this. I can do 0.5, or I can do 1 over 2. And I get 1.047, which, if I'm going to be rounding to 2 decimal places, which will be my custom here, be 1.05. Now, so that's the first basic step, is just learning how to translate between the reciprocal trig functions and the traditional ones. Now, let's think about compositions. Compositions of functions. So there are, again, two main formats. Now here, what's going to be a little bit different from this compared with what we were doing in the last section is that the two functions on the inside and the outside won't necessarily be inverses of each other. One will be like sine and one will be cosine inverse, for example. So we might have like f g inverse, or we might have f inverse of g. Now, let's consider what we're going to do in each of these cases. So in the first case, so case 1, that's inverse on the inside. Inverse on inside. What we can just do then is create a point on the unit circle that matches the information given. And then use that to evaluate the outer function. That's what we'll do in case 1. In case 2, this is inverse on the outside. Just evaluate your way out of the function. All right, so enough strategizing. Let's actually see this in play, and we'll see every combination here. So as an example, we could start with something like sine of cosine inverse of 1/2. Now, it turns out actually that this is a perfectly familiar number for us as far as our known values of the unit circle. But just in case anything was a little unsure, let's just go ahead and think about what this would mean. 1 over 2, so that means an x value of 1, and I could use an r of 2 if we were thinking about it. So x equals 1, r equals 2. And then that would be putting us like right here, let's say. And then, of course, x squared plus y squared equals r squared, the classic Pythagorean theorem. Oops, equals r squared. In circle form. And so that'll be 1 squared plus mystery y squared is equal to 4 squared. Or sorry, I mean 4. Which, when I subtract, sorry, I meant y squared equals 3. And then when I take the square root of both sides, plus minus square root of 3. And I just have to decide, do I want the positive or the negative, and I can see here that I want the positive. Okay, so then that means that the sine of the cosine inverse of 1/2 is just going to equal root 3 over 2. It's the y over r. Now, this one was known to us. This one is a familiar friend of ours, so we actually didn't need to go through so much to figure that out. Once I had it already located right here, actually, then some of my instincts might have kicked in, and I might have just remembered what the cosine inverse of 1/2 was. All right, let's try one that's a little bit harder. Let's try one where it's not a known angle. Let's start with something like this. Oops, B. So the sine of the tangent inverse of -3. So let's think about that. So tangent inverse of -3. So in other words, that means that the tangent, let's just call that theta. So that means then the tangent of theta equals -3 over 1, I could say. And so then maybe I can make that my y, that my x. Okay, well, let's try it out. So y of -3, x of +1 would put us down here somewhere. And what would the r then be? Well, let's figure it out. So x squared plus y squared always equals r squared. And so that's going to be 1 plus 9 equals r squared. So r squared is going to equal 10. So r is going to equal the square root of 10 plus or minus, and we'll choose the plus. Always choose the plus for the radius. Okay, and so then if it's the sine that we want, then it'd be a y over r root 10 over, -3, over root 10. And of course, by now we know we have to rationalize these kinds of things. So it's -3 root 10 over just 10. Okay. So the conclusion, sine of tangent inverse of -3 is equal to -3 Oops, sorry, I lost my 3. Negative 3 root 10 over 10. So that's how you do it. These are both case 1. So case 1, you start by just plotting a point on a circle, and then try to work it out from the inside out. I said unit circle right here. That's kind of our default, but actually, come to think of it, we hardly ever will actually restrict ourselves to an R of 1. So on a circle, it's convenient to be allowed to have a little bit of liberty in your radius, so that way you can make the numbers work out a little bit better. Okay, so now let's try one that involves something with the reciprocal functions. So how about let's go with a good one. How about the cotangent of sine inverse of, now this one is going to happen to be negative root 2 over 3. This one happens to look like one of our friends, but be careful, this isn't one of our friends. Negative root 2 over 3 is not one of our friends from the unit circle. Okay, so this one involves just the cotangent of a sine inverse. So the sine is on the inside, and that makes it a little bit nicer. So we can just go with y equals negative root 2, r equals 3, and then what's that make x equal? So then we'll just go through the usual stuff. X squared plus negative root 2 squared is equal to 3 squared, which is 9. And in this, the negative will cancel, and also the square root will cancel. And so this is x squared plus 2 equals 9, which means, in other words, x squared equals 7, which then means that x equals plus or minus square root of 7. And here, we're almost always going to be choosing the positives on this. And let's see, so what would that put us at? So a y of negative root 2 and an r of 3. So it's a negative y and an r. So we might as well just have that point right there. Okay. And in fact, this one has to be that point right there because that's the range of sine inverse. And so now for the cotangent, x over y is equal to root 7 over negative root 2, which, if we wanted, we can rationalize this. And I can also pull out the negative to the front, which I will. There. Right where there's more room. So pull the negative out to the front, which will be the standard operating procedure in dealing with these. I will rationalize it by multiplying root 2 over root 2, and that's going to make, so when you have two square roots multiplied together, you can just bring them both things together. So that'd be negative root 14 all over square root of 4, which is, in other words, 2. Okay, so that is how we would do that. And then if we want to go the other direction, where we have the inverse on the outside, that would look something like this. So let's say we wanted the cosine inverse of the sine of, and then what comes in here will have to be one of our friends. 2 pi over 3. Okay, well, we just evaluate this. Let's evaluate this from the inside out. So 2 pi over 3, that puts us right there. The y value of that point is is positive root 3 over 2. This is cosine inverse of positive root 3 over 2. Oops, root 3 over 2. Now we just think about that. So root 3 over 2. That is that's a famous number, and then we just try to think about where on the unit circle in the appropriate quadrants do we see those cosines, and that's a bigger value for x, so that means we're talking about the value that is over here, and so we can see that that's going to just be pi over 6. And then let's just have one that also involves some of our new friends. How about the cosecant of the cosecant inverse of the cotangent of 1/2. Okay, so let's just think about that. Oh, sorry, that's the wrong way. The inverse has to be on the inside here. Okay, so otherwise it would have been impossible, because if that inner one is not one of our known angles, we can't evaluate the cotangent of it, but we could do it with the inverse on the inside. Okay, so cotangent inverse of 1/2. Well, if I just make x equals 1, y equals 2, that seems like the easiest thing that I could do. And then we'll just let the chips fall where they may. So x squared means 1, y squared means 4, equals r squared. So that means r squared equals 5, which means that r equals plus or minus root 5, and we'll just choose that one. So, root 5, okay, and then cosecant. Cosecant, so the cosecant is equal to the reciprocal of sine, which would ordinarily be 2 over root 5, or in this case, root 5 over 2. And so, I guess that's just our answer. So cosecant of, it's the r, it's the y. The cosecant of the cotangent inverse of 1/2 is root 5 over 2. It's kind of magic that you're able to even do these types of things where you have one function and a different function, and you're able to use the inverse of a totally different function to undo something that wasn't even its original function. But it gets even weirder. So we can actually do these compositions in general and produce just algebraic expressions. Compositions using a general variable, which will just be u, to get algebraic results. An example of this, so an example here is write each trig expression as an algebraic expression in U. So that's the way it's worded. So it's always worded in your book or in the MyLab. So here's how this will work. It's not actually any different from what we were doing a second ago. It just looks kind of different. So sine of cosine inverse of u. Well, what we can just think of here is just think of making a point on a circle and letting the u stand for something convenient. So u, we can rewrite that as u over 1, and this is a cosine, so we might as well make u equal to the x and 1 equal to the r. So now we will be on a unit circle. So u is the x-coordinate, we don't know the y-coordinate, we know the radius is 1. So what that means then is, since x squared plus y squared equals 1, u squared plus mystery y squared also equals 1. And so if I solve this for y, I'll get y squared is equal to 1 minus u squared. And that means that y is equal to the square root of 1 minus u squared. And now, sine, that's y over r, so the sine of the cosine inverse of u will just be that y that we just found, 1 minus u squared, square root of all that, all divided by r, which is 1. So it turns out this composition of trigonometric functions produces this function, which doesn't have any sine or cosine or anything like that in it. It's purely algebraic. Let's try another one. How about something like this? What if I asked you about the tangent of the secant inverse of u? Okay, well, let's see what we can do. So once again, we have to just try to use what we can out of that u. So u, we just write it as u over 1. It's the easiest thing. And then each of these things is a ratio, so we'll just make it stand for whatever's convenient for us. So here now, secant, remember, is 1 over cosine, so it's the reciprocal, so everything is backwards. So if cosine is x over r, secant is r over x, which means now that our radius will be u, and our x will be 1. Oops. So the radius and the x. So then, mystery y squared plus the known 1 equals u squared. And I solve that for y. U squared minus 1. Take the square root of both sides. Y is equal to the square root of u squared minus 1. Now we look back at the original thing, and we are supposed to be making a tangent. So remember what tangents are. That's y over x. And so tangent of secant inverse of u produces now the algebraic expression square root of u squared minus 1 divided by the x, which is 1. Oops. So we don't even need the 1. And so notice it's very similar to what we just produced a second ago, but it's slightly different in that it's 1 minus u squared in the one case, and u squared minus 1 in the other. Alright, well, this is the basic way these problems will go, and now that you can do them, you can do everything that is in your 6.1 and 6.2 homework. So, I'll leave it there, and until next time, bye!